OCR. I think most of you have heard of OCR. It's essentially a AI model that captures the image of a document and then translate it back to text. And but before we start today, I want to have a quick announcement. For the Vibe coding project, can we have a quick meeting during the break? So, okay, good. So today we will do a quick recap on last week's quiz and also what we have covered in the last week. And then we will talk about the OCR evolutions. And we will be using a model just launched last month. I think it's the 29th of January. So anyone of you heard of the company Pedal? 好像叫飞掌，飞掌是is I think a company. I think I'm not sure what the relationship between Baidu and Pedal, but it seems that it kind of like the Hong Kong version of Baidu. So they just released a model which surpassed most of the OCR AI model available. So it only the size of the model is very small. It's around it's less than 1 GB. So you can actually run it in a reasonable sized PC. And we will talk about how to fine tune the pedal and the code I provide in this week will allow you to fine tune with Flora. So fine tuning the pedal model with the demo that you run will have a slight improvement because I only trained it with a few examples. So in your project, you might try to increase the number of data samples for fine tuning the OCR model. Okay, so let's have a quick review on the quiz. So the first question asks you about the HPC architecture. So actually the main purpose of this question is to remind you that please do not find a model bigger than 16, I would say 14 gigabytes of VRAM in your project. So essentially this is asking you need to train if you want to train a vision language model that requires exactly 18 gigabytes of VRAM. So load the model weights on a single GPU, excluding activation or batch data, and you assume single GPU training job without code modifications. So you can actually do it, but you need some advanced trick, such as splitting the model into half or something like this. But if you just try to fit the whole model into a single GPU, it won't run. So the answer for this one is C. So as I've just mentioned, the hardware constraints is 16 gigabytes. There is a side note that you want to also know multi-instance GPU. Multi-instance GPU refers to dividing a single GPU into multiple instances for inference. So if you have a GPU that is not as big, you do not want to divide the GPU into multiple instances because it will be even smaller. This is for parallel inferences. So it is kind of related, but not directly related to this question. Okay. So the answer for question 1 is C. And the other question for Slurm job scheduling. So if you submit 3 jobs to the GPU partition using batch in this order, the question is asking which job will terminate or complete last. So the answer for this one is D. The derivation is actually not as straightforward as you might have think. So the initial submissions at time 0 would be something like this. So all 3 jobs submitted to the HPC server with the job ID. So this one submit first, and this one submit second, and this one submit third. And then 1 and 2 of course starts immediately because we have 4 GPUs. So these 2 will start immediately and will occupy 4 GPUs. And the third one, which because of only 1 GPU is free, it enters pending states, waiting for resources. And then for the first hour, it completes, and then it now have 2 GPUs, which is free. And then after it is finished, the job, last job, which was waiting at the front, will occupy the 2 GPUs. And then jobs, last jobs has a straight time limit of half an hour, so it starts at 1. Also, it will reach, it will be killed if it is longer than this period. And finally, you have the job 308, which starts at 0 and lasts for 2 hours. So the result would be 308. But it is not as simple when you are doing your project, because the Slurm priority will also consider the frequency of job submissions. So it will have something like priority or resources noted in the reasoning of your queue. Okay, so any questions for the first 2? No? Okay, so the third question is quite simple. You have a PyTorch tensor, which is already loaded on GPU. So X is already on GPU, and you want to compute the E of each row and return a CPU NumPy array. So which mode is the most efficient? Because this is already in the GPU, you directly compute the mean and load to the CPU and convert to NumPy. B is obviously not efficient. It uses GPU to do the computation. And of course, this one also forces the computation into CPU. So in D, when you see this syntax, you can know that you are using a for loop, which is you do not need to use for loop in GPU. So as what I've mentioned in the first lesson, you can directly call the GPU library and execute all the computation all at once. So you do not need the for loop here. So that's why the answer is A. And for the next question, which is the 4th question, if you train a BPE tokenizer with a vocab size of 1,000 on a medical corpus, after training it tokenized the phrase, I don't know how to pronounce this, is thoroughosis, something like this, and you get 3 tokens. So what does this tell you? This tells you the corpus didn't contain thoroughosis frequently enough to merge it fully. So just a quick reminder of how the BPE algorithm works. Because after one merging of a single token, the next token that is going to merge is based on frequency. So it will be searching for what's the most frequent pair and then try to merge it. That's why if you do not see a token a word being merged as one token, it just means that it is not frequent enough in corpus. Okay. So the fifth question in the quiz is you try to train your training script crashes with torch CUDA out of memory. And you check in the media and you see something like this, which strategy will not help to reduce the memory usage? So the answer is B. So if you use torch CUDA anti-cache after each training step, it will not help. You have to reduce the batch size and you have to enable gradient checkpoint or maybe use mixed precision training. So the CUDA out of memory error is often seen as torch CUDA out of memory in PyTorch. It is a runtime error that occurs when program attempts to allocate more memory on NVIDIA GPU than it is available. So it is typically happens during GPU acceleration tasks. Okay. So because if you empty the cache, in the next iteration, actually the PyTorch will clear the cache for you. So clearing the cache will not help. Okay, so because of the, you might be using the prompt vibe coding or in your project. So make sure that you guide it, you guide your vibe coding, your AI agent coding with these sorts of instructions. Okay. So the next question is talking about that if ever your cluster has two partitions, in your project, if you are going to do using AI to code, make sure that you give it the correct partition name. In our setup, we haven't set up a partition for CPU. So if your code does not run, sometimes maybe it is because your code generated by your AI does not know that the partition is called something like GPU, okay? And there are no CPU partitions. So, but in here the question is asking if there are two clusters in your partition and you submit a job, what happens? So a job runs on the CPU partition without GPU. The job automatically move to GPU partitions since it requires GPU, or the job fails immediately with error. So CPU partitions is no GPU. Okay, because you are requesting a partition for CPU, but you also request a GPU. So it's a bit confusing, but it is sometimes, I don't know why the AI generate code sometimes with this sorts of mistakes. Okay, so this question is asking about the coda-only transformer. So it's asking what's the purpose of causal masking in self-tension mechanism. And the answer for this one is to prevent the model from attending to future tokens during training. So last lesson we talked about sequence-to-sequence attention. And remember the reason why we have to zero out others in the attention matrix because we do not want the model to look into future tokens. So similarly, this is also the purpose of causal masking attention mechanism. So in decoder only transformer, the decoder only transformer like GPT-2 also masking is also called autoregressive or lower triangular masking, because when you see the attention matrix, all the ones are highlighted in the lower triangular mask. It's applied in the self-attention layer. So what I mean by lower triangular mask is lower triangular mask. So something like this, lower triangular mask. This one is actually. So remember last time, I asked why there are zeros in the top left of the triangle of this attention matrix. It's because it will only look for the word that has been generated, but not the future tokens. I think Fang Zheng answered this correctly last time. So this ensures that during training and inference, each token is in a sequence that can only attend to itself and predict tokens. Okay. So for the LoRa fine-tuning, you have to understand this part confidently, because during the project you need to calculate can you actually train your model using LoRa in our server. So the question is asking you fine-tune a GPT-2 with LoRa using our 16. Anyone record what is R? Anyone record what is LoRa alpha? I think you got quite a lot. I think you got it right in the quiz. Okay. So the R refers to the dimension of here. So remember matrix multiplication. So assume this step is the LoRa matrix. What's the R? So what is R? So what is the number of R in here? If this is, you have two options. One is 3, the other is 4. So if you think the answer is 4, please raise your hand. 4. The answer is 3, please raise your hand. Okay, I thought you got this right in the quiz. Okay, so for this demo, the R is 3. Does anyone tell me why the R is 3? Why the R should be 3? Or why the R is 4? So, okay, let me go over this, and we will do this again. So, in this question, R is 16. So the target attention projection layer conveying Q project and V project and combine into a C attention module. So the question is asking how many trainable parameters does this add approximately. So the context is GPT-2 has 12 transformer blocks, each with hidden size D is 768. The GPT-2 query and value projections are part of combined attention module. Okay. So you start off with tokenizing the representation into a 768 dimension vector. Okay, so given by the question. So the D size is 768. For a sequence of T tokens, the input of the input shape is T times 768. So in this diagram, what is the number of rows? What is the number of rows? So if you think the number of rows is 768, please raise your hand. If you think the columns are 768, please raise your hand. No idea. Okay, so if you write it in this format, the rows is often written in the far left. Okay, so you can remember is row multiplied by columns. So row is number of rows. So you have T, number of rows, and 768 columns. Okay. So T refers to the sequence length, also known as the context length, also known as the context window. So the context window, if you remember from last semester, context window of AI models. Or latest AI model. So now the context window of the latest AI model with leading is Google's Gemini. I think it's not 1.5. I think it's 3, something like this, supporting up to 2 million. So the number of rows in here would be like 2 million. Okay. And the embedding size, do you know what the embedding size are? Do you know what the common embedding size are for now? So do you remember what did you use for the last semester for the project? What's the embedding size for your project? 1546. Yes. For the Nova, it is 1,538. For GPT, it would be most likely to be 1,024, if I remember correctly. So this would be very long, and this would be very short for nowadays. So, and also the same case here. So the dimension, this is the input hidden state. So for each row, it represents a single word. So each row is one token embedding, and GPT-2 small use this embedding size. So you will be passing, because you will be computing the Q, K, and B, remember? You need to compute the Q, K, and B. For the GPT-2, it uses a single combined layer. So this would be the matrix Q. This would be the matrix K. and this would be the matrix V. So one thing you have to notice is this central matrix here does not depend on T, which means this matrix in here will not be depends on the window size or the context length. Therefore, when you do LoRa fine-tuning, it does not matter if the T window size is very huge. The only thing that is matter is the embedding vector. So you can see, you can understand why some large language model try to limit this dimension of the embedding size to a very short vector, because if it is long, the computation will be huge. So instead of separating it, okay, these are just some configuration of the GPT-2. So you have the so what you want to fine tune is the middle one, right? So what is the dimension of the middle one? So it is 1768 multiplied by QKB. So you have to have 3 of them add together, because you have for the attention you have to compute all 3 matrices, so times 3. Okay, any questions? Okay, so after this, you split into three kind of QKB activations. So with these activations, you compute the attention score. But luckily, the part that we are going to fine tune does not depend on T. Okay, so we do not have to know about the T dimensions. So back to here, for LoRa, because what LoRa is trying to do is to put an adapter which kind of it needs to make the same size as this one, right? Anyone remember what LoRa is? Okay, we spent so much time talking about LoRa. Okay. So So the core idea is to make a matrix that is compatible with this matrix size, because we do not want to change all the weights of this matrix, right? So we have to reduce the number of elements in the matrix. Remember this. Remember matrix multiplication. Remember we did this. So what's the output dimension of this matrix? This 2 matrix multiplication. What's the output dimension of this 2 matrix? is 6 by 6, right? So in LoRa, what we try to do is we do not want to fine tune all the parameters in here. In LoRa, we will use this trick because this got way less elements, right? Okay. If I increase this one, that one. Okay, this got way less element than the full matrix in here. So the core idea of LoRa is we only fine tune this two part of the matrices rather than tuning this large matrices in order to achieve weight training, fine tuning the model. Okay. Okay, so let's go back to this slide. So what's the R? What's the R for this diagram? Okay, 3. Someone said 3. Okay, good. So because the R controls the dimension that we're trying to reduce, so is this one and this one doing a matrix like this one. Anyone say 4? No. I think this is a trick question. Okay, let me go through this, and I will review the answer at the end of the lesson. Okay, so I think most of you got this question right, so I think I will just keep going. Okay, so the LoRa rank, instead of fine-tuning that's what I've just said, fine-tuning all the parameters, we're fine-tuning a much lesser matrices, so A and B will make something up like the middle part. So we have matrix A, matrix B. Similar in here, we have matrix A and matrix B. So this part is the matrix A, this part is matrix B. And then we add all the parameters, we count all the parameters and multiply them as well. So in this case, R is 16, so you have your embedding size multiplied by 16. So this is the shape of A, and then shape of B, and then you add them together, and then you get the final 12 blocks. Okay. So question 9. Hugging Face dataset library. This one you do not actually need to worry too much about because I do it for you. Okay. And auto-regressive text generation. When you set the temperature to 0, what will be sampling strategies does this include? Of course, it's really decoding. Because when you, there is kind of interactive demo. When you shift the temperature into the far left, the probability distributions will always shift to the top one. So it will be a 3D decoding. Okay, so question 11, batch processing with aspect. These questions actually, I think, okay, so I've only taught you to do the S batch. So I haven't taught you how to do an S run because it will spin up an interactive GPU environment. If you do not close that properly, you will be stalling other students using the server. So essentially, you should not be able to answer this question, but the core idea is you always submit separate SBS jobs to the server, and please do not use the srun command because you will stall other students to use the server. Okay, so this may be relevant, but these kind of directory will change from time to time. But sometimes you will encounter something like permission error. If you encounter something like permission error because it is that you cannot directly write to these sorts of directory, I can install the model and dataset for you. But if you are going to set up an HPC server, you might need to know this kind of stuff. Okay, so GPU architecture and some basics. So in your HPC server cluster has an NVIDIA 16. Each has partition like 16 gigabytes of VRAM and no NVLink support. And the question asks you about if you want to train a model that requires 12 gigabytes of VRAM, what's the best solution? The best solution is to reduce the batch size to, or use gradient checkpoint to fit into the 16 gigabytes. The main point of this question is to point out that NVIDIA A16 do not support NVLink. So if you are going to buy a GPU for your company that will require to run multiple large model, please do not buy A16, NVIDIA A16. The A16 GPU only for use, if you're using, if the purpose is for education, I think it's okay. Because the main job of NVLink is to allow cooling. So you can, you might heard that some, in some configuration, you can set up multiple GPU with say 4090S, but it is using PICe for communication, which is not the same as VRAM. So the main point of this question is to make you realize that if you are going to purchase HPC solutions for a large model training, you need to consider NVLink, so GPU that support NVLink. So I think I'll go through these questions. The idea is just to let you realize that special tokens can be added after the tokenization. Okay, this is for your project consideration. So if you are going to train it for 10 hours and you want to save it, say, as often as you can so you will not lose any progress. So if you fine tune on a small data set, this might be relevant when you're writing the project evaluation. So if you fine-tune a pre-trained vision language model on a medical data set with 1,000 training samples, using LoRa after training, if you evaluate the base model with the accuracy of 45%, and the fine-tuned model with the accuracy of 46% accuracy, with a 51% of repetition rate. So it's keep repeating itself. And one is with the rank 8. And so which which is the best explanation for why rank 8 outperforms the rank 16? Is because rank 8 provides better regularization, prevents overfitting on a small data set. So the key term here is overfitting. So this one is essentially checking whether you have used AI or not, because I have not covered this, and it is also not, we have not talked about the random seed problem. So this is for checking whether you used AI. So if you got this question right, most likely you will be using AI. Okay. But for your interest, the array is something related to the slur array class ID, and you need to set in the in your batch file using Python train C, something like this one. For the node parameters in our HPC setup, we have only one node. So effective batch size and gradient accumulation. So just a quick refresher on the gradient accumulation. Essentially, if you do not have enough memory for a large batch size, you need to use gradient accumulation to make the effective batch size larger. So the gradient accumulation addresses this by breaking large effective batch size into smaller mini batches. So this one is fairly simple, but I'm not sure why most AI got this wrong. Perhaps they need to look into this paper. So this is the original definition of the top P sampling. It is just essentially testing whether you will add the final map into the consideration or not. So remember, we do top P sampling. We calculate the commutative probability up to 0.9. So if you add these up, it's larger than 0.9, you will not consider the next word. So this is just the formal definition of the nucleus sampling. It includes a larger or equal to. So this sign is the formal definition. So the answer is A. Okay, so I think this is also the AI tracking questions, but I think you should be able to, for human, you should be able to select the correct one. I think no one got this question right, so I speculate I think maybe you used AI to answer this question. I'm not sure, or this question is too difficult. So the fine-tuning model use LoRa using the rank out. So after training, you want to double the capacitor without retraining from scratch. What's the best approach? I think because the AIC doubling capacity without retraining from scratch, and then B is also because it also mentioned retraining from scratch. That's why I think most AI got it wrong. But if you look into the question, you saw this. What is the best approach, right? So the problem with setting R into 16 and continue training from the same R to 8, most AI will pick 8. But the problem with 8 is that if you look into the matrix multiplication, it will not work because the matrix dimension is not correct. So for R equals to 4 and R equals to 8, these two matrices cannot be directly swapped. That's why A does not work. You can try it with the code. So because of this problem, A does not work, and B won't work. You can load assemble is possible, but does not double the capacity of a single adapter. And for the C LoRa alpha scaling is not right. So it just affects the learning dynamics, but does not change the parameter or counter presentations. Okay, so any questions regarding the quiz? No, okay. So let me go back to the rank problem. This is actually very important, so I want to go through this once more. Let me copy this slide. Okay. Okay. So when you compare these two slides, okay. First of all, can anyone find the R in here? Okay. So what's the R? Okay. What's the R? Okay. Maybe I will click into this website. So the R, which refers to this part of the dimension, and if your checkpoint is mismatched from the current model, you cannot actually train it. Okay. So the R in this configuration is 4, right? Okay. Okay, so what's the R in here? 4, please raise your hand. No? 3, please raise your hand. 3? Okay, why 3? Okay, let's go through this. So in here is 4, right? Here is 4. Why do you think it's 4? Okay, so the column of the left matrix is 4, right? The column of the left matrix is 4. So how about in here?
4.
Okay. Okay, so how do we find the R in here? Someone told me just yet we want to count this, right? 1, 2, 3, 4, right? We have 1, 2, 3, 4, so this is 4, right? Okay. Oh, okay. count this, right? 1, 2, 3, 4. Okay. So it's 4. So for Laura, because the main whole idea is we want to make a smaller matrix, right? Make a smaller matrix. So R should be small. But of course, you can make R to be large, but will not serve its purpose. Okay, so any more questions regarding the quiz? Okay, good. So let's have a quick review because we have mentioned sequence to sequence. So we have to, I've mentioned sequence to sequence array in the last lesson. So I want to go through it to make sure everyone understands what is sequence to sequence attention. Okay, so you have learned self attention, you have learned cross attention, right? I'm just going to remind you what sequence to sequence attention. So I think I will quickly go through this and I will give you a break. Okay, so from the raw image to text embedding. So essentially, we have the raw image, which have a raw image tensor, and we have one batch. So the first, you see the first number in the code usually refers to the batch size with 3 channels, RGB, red, green, and blue. And recall last lecture, we want to split the image into different patches, right? So with height is 4, and also okay, so this is 4, and this is 4. Okay, so split the image into different patches. So now we have different patches, and we try to flatten the patches into a single array, and then project it into the image embedding. Okay, so in here we try to project the patches. We try to project the patches into the image embedding. And for each image embedding, we add a special token that is almost like the beginning of sentence token for text. So this is just a, you can say, artificial made token for images. It tries to inform the model that, in here we are going to put images after this token. Okay. So for the text part is fairly simple. We break the text into tokens, and we use the embeddings to force them into the text embedding array. So after this, we have a series of token vectors, and then we do the, for each, for the, this refers to text. So for the input, and we are trying to do the cross, the attention mechanism. So we forced it into QKB into 3. So if you think about this, if you using this whole sequence and force it into QKB, the first part would be refers to the image, and the second part would be refers to the text tokens. So this part is image, and this part is text. And then we will try to do attention. So in here, we compute the query using the text, right? So after projecting the image, we will compare the image with all other images, and we will compare the image with all text, and we will, for the text generation, because it cannot see the future text, therefore we have this lower triangle attention shape in here. So after the masking, these are the all the attention score. After the masking, you only get the attention weights in the results of this one. Okay, so this first top left side of this matrix refers to the image to image attention. So you can think of this as not self-attention, but image to image attention. And this part is for image to text attention. So we will be masking this part because the image will not see future text anyways. So we will mask this task, mask this image to text attention. And then for the bottom left corner, we have the attention for image to text attention. So essentially, for this one, this is the actual question. This is for the extra text that it will be generating. So you can see the questions. The first text of the generated text refers to the question. And so this part is the question. So it is essentially asking, using this question, cross-attend to the image itself. So it's like, is this an apple, the image? We will do a cross-attention in this part. For the generation task, it will generate, so in here it will be like, this is apple. So the generated text will be, this is apple. And why this is a lower triangular form? It is because you cannot see the future tokens. That's why it is masked. So let's go through this once more. So this is image to image. So all the image tokens can see all other image patches. So in here, because we have not actually generated the answer and the future tokens, because so this will not have any effect on the image, right? In here, because we are asking the questions like what is in this image to the image itself, so this part we allows the attention mechanism to work on it. And the bottom right is the regression mechanism. So we will force the new generated text to see only the question and the image. So at the end, you will see this one. So for the for this part of the text, for this part of the image, we can attend to all other patches of image. For the first generated text, it can see the image and also the text, and also the second text. Okay, so it's not shown. Okay, then the mechanism continues, which just essentially forcing the generated text into a softmax probabilities to pick the words. So I think I would like to pause here and take questions during the break. So I think it is a good time for a break. And yeah, okay. Okay, so for these attention mechanism, if you do not understand the mechanism, it will not affect the project. But I think it is essential to kind of know what the model is trying to do. And but I think for the project, I think you can kind of get away with this understanding for the project. But for the project, it's essential for you to do the evaluation of the model, but instead of tries to change the structure of the model, unless your project want to change the attention mechanism, and you can explain the reason why you want to change the mechanism. So this, the whole diagram, you can build it in this website. So these animations are just playing the matrix multiplications one by one. So you can click into this and see which one is attended to which one. So I think I did not specify in here. So I think part of the text in here is the question itself, and the part of the text in here should be the answer. So when you look back into this one, tokens so this is the image token, and these are the question tokens, and for each one, for the question, you can kind of see the tokens that are already generated, but not for the tokens that are not generated. Okay.输出之后再还原。
它先经过卷积层、石化层，经过几个卷积层跟石化层之后，它的那个像素的大小就会压缩，然后最后再最后生成像再这个要两项。就是把它的主要的 features 提取出来之后，再加上空间的位置关系，然后再经过卷积、石化、卷积、石化之后，它的那个像素降低，但是它的那个核心的特性也保留，是这个逻辑。
应该不是，应该不是这个当然今天讨论的那个模型呢，其实是有用那个转化成的，有用 人机上就是那个 CNN，就是有 CNN，但是这个 mechanism 这不是 CNN 的那个 mechanism， 所以刚才讨论那个其实是上一课。刚才讨论那个其实是上一课的那个 review 来的。我想想一下。
幾版啊？
咩另一個係為咗食嗰張相。
理解。Is it image token?
对这个，刚才讲那个其实是这个，就是为什么那个so what we have just talked about, what we have just talked about is just this is essentially refers to this matrix. So what it does is try to do the, you remember self-attention, right? So in self-attention, all the text in here, all this, if you remember, say GPT-2, all the attention will be reversed to text, correct? So for the masked self-attention, you have a triangular attention matrix, right? So let me show you a self-attention. Okay, so let's go back to this model, right? Okay, this one is. You're familiar with this one, right? Okay, so in here, it has a term for multi-head attention, and also a term called masked multi-head attention, right? It has two attention mechanisms. One is masked multi-head attention. One is multi-head attention, correct? Can you tell the difference? Okay. This is last semester stuff. So can anyone tell me what is masked multi-head attention and what is multi-head attention? Okay, so let me show you what is masked. Okay, let me first show you what is attention. attention matrix. Okay, so this is attention mechanism. Okay, so this one effectively explains. So the attention mechanism is that you have a questions and a key. Remember, you have a questions and the answer, and you calculate what's the relationship between the questions and the answer, right? Okay, so this is attention mechanism. What I meant by mask is that because of the auto-generation mechanism， 就是说它 generate 一个字by 一个字，对吧？然后它就是一个字by 一个字，所以它还没有这个字之前是看不到之后的那个字。So let me repeat it once more in English. So when you generate these tokens one by one, you have to generate it first before you can actually see the attention mechanism. So you cannot see the future tokens. That's why they invented the masked attention mechanism, which essentially zero out all the attention mechanism of the upper right. So this one, they covered all of this block so that the questions that has been asked will not be able to see the tokens that is not generated. So for this word, like if this is asking, this is an apple, right? This is a very delicious apple. So this cannot see it's a very delicious apple. And is can only see this. So the word is in here cannot see a very delicious apple. Okay. So this part is clear. Okay, so now go back to this slide. So now go back to this slide. Using the same paradigm, because image can see all other image patches, right? Because it do not have this sequence of generation problem, okay? So image can see all other image, and but the image cannot see the newly generated text. So for this text, this is already generated because of it is a question. It is formulated in a question. So this question text asking what is in the image, and in this part is follows the masked attention mechanism, which allows it to do the auto regression task. Okay. Okay, so I will take a quick break here, and for the vibe coding project, can we have a quick video?
Very short. 咁我停一停先。